All right, let's do some physics one. So, again, usual disclaimers. These are just exams I write to support students. I'm not College Board, although I have written items for them, so I hope the style matches. Can't guarantee you the difficulty does, but I tried my best to kind of spread the content around. So, if you're here because you want more mechanics practice, that's great. Any question that doesn't involve fluids is in the scope of C mechanics, but just realize that since you can't use calculus, most of the P1 questions are going to be easier than your average mech question, although a lot of them are still good. So let's start. So hopefully, since I tried to make this more reflective, like I tried my best not to just make 40 hard questions, that I finish in the correct time period instead of like going over time like I have in the past. So let's start. All right, first up, starting strong with some fluids. A fluid travels through the horizontal pipe shown below. The pipe is wider at x than it is at point y. Which of the following correctly compares the speed v of the fluid at each point with justification? So we're trying to figure out if the fluid speeds up or remains at the same speed. So anytime you're talking about fluid speed, there's one of two ways to do it. It's either Bernoulli, which is energy conservation, but you'll know it's Bernoulli because there's some sort of height change. So the other thing, the easier one, is just continuity. So what we know is that the volume of water passing through the pipe every second has to be a constant. I'll actually write this as volume, just so we know it's not V. Volume divided by time has to be constant. And we actually do have an expression for that. The volume flow rate is area times speed. So we come up with the continuity equation that says A1V1 equals A2V2. And in this case, instead of 1 and 2, let's call our moments in time x and y. And we're given in this problem that the area is wider at x. So that means my area is sort of shrinking at y. So the velocity must go up proportionally to maintain that same product. So we can see that our fluid is going to speed up because, well, we use the continuity equation. That's just B. And I rate these on a 3-star scale. Try to make it kind of like a bell curve where there's a couple level 1s, a couple level 3s, but most are level 2. All right, in the scenarios described below, a block of mass m travels along a frictionless surface at a speed v towards a barrier. And we have two different barriers. One barrier is made of metal, and the force exerted is F1. And the second scenario, the barrier is made of foam, and the force is F2, which, because it's made of foam, is less than the force exerted from metal. So we're comparing the collision time and the impulse delivered to the block. So anytime you're talking about collisions and time and force, we want to use impulse momentum theorem, which says the impulse, by definition, is the momentum change. So if we're looking at this, it's key. The key detail is that we're completely stopped by the barrier in each case. So if we're completely stopped by the barrier, that means that we have the same delta V. So we have the same momentum change. So our impulse is the same. So this is, I call this like the egg drop problem. Whenever you have a constant impulse and have to figure out how to build your collision. So now we can use the impulse momentum theorem that says momentum change, m delta v, is equal to the average force exerted times the time. So if we know that the impulse is the same and we have a constant is equal to f delta t, well, this looks just like the continuity equation from last time. So for our metal, or sorry, looking at the foam exerted a smaller force on the block. So that must mean the contact time was longer, right? This is just like an airbag, right? If you have to get stopped, the force is less if your time is extended out in the constant impulse case. So that is why the answer is C. I thought that was level 2. All right, small sphere is attached to a string of length 2.5 meters, and we give it a small displacement, releasing it from rest at t equals 0. which of the following could represent the angular velocity of the sphere as a function of time? So we have these very similar looking sine cosine graphs. Just notice the scale is different on the axes. So first of all, notice that we just have to make two decisions. One, we have to decide what is the period, because we have, it looks like pi and 2 pi as our choices. And we also have to decide, is the angular velocity 0 or not 0 when we release it? Well, we release this from rest. So this means omega is equal to 0 at t equals 0. So then we just got to figure out the period. And, well, how convenient, we do have a formula exactly for that. The period of a pendulum is 2 pi times the square root of L over G. And our string length is 2.5 meters. G is, of course, 10. Please use 10. I know 9.8 is more accurate, but we make the numbers work out with 10. So that gets us 2 pi times the square root of 0.25, so 2 pi times a half, which is pi. So we have a period of pi and an initial velocity of 0. So that corresponds to C. Because you had to compute the period, we bumped that to level 2. All right, a block of mass m is attached along a frictionless surface to a spring with force constant k, as shown. The spring is compressed a distance from equilibrium before being released, and the maximum speed of the block is v. If the total energy of the mass spring system is E, how much energy is stored in the spring when the speed of the block is half v? Okay. So you can do this with or without math. I think I'll do it with bar charts first. So what's important to note here is that we know that the kinetic energy plus the potential energy stored in the spring is always going to be this constant E. So what that tells us is that if I draw my bar chart at this moment in time, well, we know that we're going to get some sort of kinetic energy. But what is kinetic energy? Well, kinetic energy is 1/2 mv squared. So if our speed isn't the maximum speed v, but it's instead half of the maximum speed, our kinetic energy would not get halved, but it would get halved squared. So 1/2 times 1/2 is actually a quarter. So that actually means at this time, our kinetic energy is not half of its max value, it's actually a quarter of its maximum value. So just to make our bars work out, if a quarter is in kinetic, then that must mean 3/4 are in the spring. So that's kind of how you do that with a bar chart sort of line of reasoning. But you could sort of do this directly, where you know that E total is equal to 1/2 mv squared. And if we look at the time given, we're actually given the time when v is v over 2. So we get 1/2 times m times v squared over 4, which is equal to 1/4 times the quantity 1/2 mv squared. And we see that that's a quarter of the energy again. So both ways get the right answer. This is just a lot more work to show that the kinetic energy is a quarter of the total at this time. So I did think this was hard. I ranked this level 3 because there's a couple sort of things you had to see going on there. All right, some more fluids. A hole forms along the side of a tank, which holds a 1.8 meter tall column of water, as shown. If the hole is positioned 1.25 meters below the surface of the water, calculate the speed of the water upon exiting the tank. So this is about speed, but it's not a narrowing pipes question, so it's not continuity, this is Bernoulli. So Bernoulli's equation tells us that the pressure plus rho GH plus 1/2 rho V squared is a constant. So we just take these terms at both times. Now, if you know Torricelli's theorem, you can get this done actually quite quickly because you'll see that we get a pretty good result out of this. So first of all, anytime we do Bernoulli, we have to decide on 2 locations to do it at. So I'm going to pick the top of the tank and the hole. Then we need to define kind of our heights for everything. So my second height is just going to be whatever this distance is. So it's the difference between 1.25 and 1.8, although you'll see this actually doesn't come into play. 0.55. And then we can also notice that since the hole is open to the atmosphere and the top is open to the atmosphere, those pressures are the same. So the pressure terms cancel because it's only change in pressure that matters. And also there's no speed at the top of the tank because the water's still at the top. So all we have to do is just start plugging in. So we see the densities cancel. And we end up getting 1/2 V2 squared is equal to G times H2 minus H1. So we end up getting that V2 is just the square root of 2G delta H. So it sort of looks like that just standard energy conservation question, where if you fall a distance H, what is your speed? So then we can just plug in 2 times 10 times delta H is actually just 1.8 minus 1.2, 1.8 minus 0.55, which is 1.25. And if we do that, we get, let's see, 12.5 times 2 square rooted, 5 meters per second. So if you knew Torricelli's theorem, you could get this done in like 2 seconds. It's just square root 2gh. But I thought it was important to derive it. All right, consider the following 3 objects. Object A moves at constant velocity v for time t. Object B accelerates uniformly from rest to a velocity v in time t. And object C slows down to rest uniformly from velocity v in time t. We're going to compare the distance traveled by each. So there's a really easy way of doing this. So since we have uniform acceleration, we just know that the distance traveled is just equal to your average speed times the time. So if we're looking at the average speed here, this average speed is clearly v, because it's just v all the time. This average speed, well, I start from rest, I end at v, so I average the speeds, and I get v over 2. Then for my third case, if I average the speeds, I start at v, I end at 0, there's 2 speeds, I still get v over 2. So in each of these cases, we see that the constant speed of v is v the whole time. So that one's going to win because there's no other speeds slower than v. And then the other 2 cases, yeah, one I'm speeding up, the other I'm slowing down, but they're equally above and below the sort of midpoint at the same amount. So B and C tie, and that is less distance than A. I thought this was an easy level because you just had to look at the velocity comparisons there. All right, a block is traveling on a rough horizontal surface as shown. The kinetic energy of the block is K at x equals 0. Upon reaching x equals x naught, the kinetic energy of the block is 3/4 K. What's the kinetic energy of the block upon reaching 2x0? So what we're given is that at this point in time, our kinetic energy is K. And at this point in time, our kinetic energy is 3/4 K. And we're interested in finding our kinetic energy when we pass this next tick mark. So we have to think about where is our energy going? Well, it's a rough surface. So we have to use the work kinetic energy theorem. Work is what is causing our change in kinetic energy. And what is the force that's taking that? Well, we know that delta K is going to be equal to the work done by friction, which is equal to negative frictional force times the distance. Negative because it's stealing energy. And notice this is actually linear, right? This is actually linear with D. So the work done by friction here would be negative FD. The work done by friction here would be negative FD. So I'm just stealing another 1/4 of my kinetic energy. So this would be 2/4 K, or 1/2. I think I said this was level 2. So you just had to see that work done is just linear with displacement. So every one of these sort of intervals, I steal FD worth of kinetic energy. The speeds don't follow that ratio. The speeds have a square root relationship in there. All right, satellite is in circular orbit around a planet. Which of the following statements are false? The mechanical energy of the planet satellite system is constant. Well, we know that that's true. Because I know that K plus U is equal to a constant because there's no external forces. What about kinetic energy? The satellite's kinetic energy is constant. Well, we know that kinetic energy is equal to 1/2 mv squared. And if you're orbiting in a circle, that's uniform circular motion. So this will also be constant because my speed does not change in a circle. The satellite's angular momentum about the planet is constant. Well, in circular orbit, we have this quantity, right? mvr. I actually should say mv perpendicular times r. And the satellite's mass is always the same. Speed is the same in circular orbit. Distance is the same in circular orbit. So we don't even have to do any cross product shenanigans. This is also constant. And then by elimination, the satellite's linear momentum is constant. So this is just quite tricky because we have to remember that momentum is mv. So yes, my v is constant in magnitude, but I'm constantly changing direction. Versus here, this sort of angular momentum is sort of out of the page or into the page, so that direction doesn't change, but the linear momentum does. And another way of seeing this is there is a net force acting on the satellite, right? It's gravity. So if you have a net force, you're going to be changing your momentum. So because you had to evaluate all of these, I've said this was a 3-star. All right, a spherical star of radius r rotates with angular speed omega. It collapses under its own gravity to radius 1/3 r. What is the new angular speed of the star? Well, anytime you're talking about this sort of collision, I call this the figure skater. Anytime you have like a changing radius of the same object and you're spinning, well, that's going to be conservation of L. So we know that the angular momentum at the start is equal to the angular momentum at the end. And for a rigid body, angular momentum is I omega. So we just need to figure out what happens to I to figure out what happens to omega. So the radius shrinks to 1/3 r. And you don't need to know the shape constant, but what is important to remember is moment of inertia is quadratic. So these moment of inertias always look like some sort of shape constant times mr squared. So if my radius shrinks by a factor of 3, that means my moment of inertia is going to shrink by 1/3 squared. So then to compensate, if I goes down by 9, that must mean omega goes up by 9, or 3 squared. So 9 omega is the answer. I thought that's 2-star because you had to get the quadratic dependence. Because if you know this is like the figure skater, you can know that the answer is going to be the speed up ones, but the quadratic factor is the tricky part. All right, the blocks shown below are attached to a spring by a pulley. We have just sort of our classic modified Atwood here. The blocks are released from rest and moved together. Which of the following compares the magnitude of the net force exerted on each block with justification? So it's either greater on block 2, which is the 2m block, or it's the same on each. So anytime you have a system, what is the same about the system? It's always going to be the same acceleration, so therefore it's the same velocity. Because everything's connected. So if the accelerations were different, this string could not remain connected. So it's always true that these systems have to share acceleration if they're moving as one connected body. So it's the accelerations that are the same. And then we just look at the net force. So we know that the acceleration which is equal to F over M for any given object, must be the same. So what that means is that since F over M is equal to a constant, that means if block 2 has a larger mass, there must also be a larger force exerted on block 2 to give it that same acceleration. So that would be answer choice C. I think I gave this 1 star. Oh, it's not that one. It's A. Sorry. The other justification, like, yeah, it's true that a horizontal surface only exerts a force on block 2, but that's not a net force. The normal force from the surface does nothing. All right, car crash. Block 1 moves at speed v in the plus x direction. Block 2 moves at speed 2v in the minus x direction. The blocks collide at x equals x0. Which of the following intervals must contain x0? So is it on the 1v side? Is it exactly in the middle? Is it on the 2v side? Or do we need to know the mass? Well, there's a couple ways of doing this. The easiest way of doing it, actually, is just sort of thinking about who's going to reach the middle first. So if I think about it, they're the same distance away from the middle, but the 2v block moves faster. So the 2v block is going to reach the middle before the 1v block does. So that means the collision site has to be over here somewhere. I thought this was an easy one. Now, there's tons of ways of thinking about this. You could take a relative velocity approach as well and see that the gap is closing between them at 3v. You could also graph it. This is just 2 lines crossing. Nice ways to do this. I like that question. All right, a block of mass 4 kilograms is released from the top of a ramp of height 3 meters. The block then moves down the ramp and reaches the bottom of the ramp with 100 joules of kinetic energy. What is the coefficient of friction between the block and the ramp? So this is going to be some sort of work energy problem, right? Because we're talking about energies and friction. So anytime there's friction and energy, we need to figure that out. So once again, please use bar charts. If you're not a bar chart like person, realize it is super helpful for problem solving. It allows you to really visualize what's happening. So at the start, my block is stopped. So all of my energy is due to the potential energy of the black Earth system. So that energy is entirely UG. And actually, we can work out what that is, because UG is MGH, which is 4 times 3 times 10, which is 120 joules. So my original energy budget is 120 joules. Then, if I look at what's happening at the bottom of the ramp, well, at the bottom of the ramp, it says there's 100 joules of kinetic energy. So notice that energy is not conserved yet, because now I only have 100 joules of kinetic energy at the bottom. So friction must have stolen exactly 20 joules of the system's energy. So once again, it's just going to be a work energy theorem now. So work energy theorem will just say that the work done, well, actually we did the delta K part. So we're just going to say the work done by friction in absolute value is just the frictional force times the distance that that force acts upon. So since we are using kinetic friction force is mu times normal force. And then we multiply by the distance along the ramp. So what is the normal force acting on this block? Well, this is our usual sort of inclined plane system. So we know there's a mg sine theta force pulling us down the ramp. There's an mg cosine theta force pulling us into the ramp. So therefore, the normal force must exactly balance the cosine component. So this is mu k times mg cosine theta times d. So we can just start plugging in now. So we have our work done by friction was 20 joules. We don't know mu k. The mass of the block is 4 kilograms. G is 10. Then we have cosine theta, which is cosine of 37 degrees. And then we have to figure out what d is. So d is not actually the height, it's the slant length. So if we work this out, you would see that this side is 4 meters. It's a 3, 4, 5 triangle. So we have to actually multiply by 5 meters there. So we'd get 20 is equal to cosine 37. That's 4/5. So 20 is equal to 160 mu k. So mu k is 20 over 160, which is 1/8, or 0.125. This is probably the most time-consuming, difficult item on the entire test. It's definitely the most involved. This is obviously a 3-star. All right, 2 identical spheres are suspended by a rope in 2 different liquids of lower density than that of the sphere. So in scenario 1, we have a less dense liquid. In scenario 2, we have a more dense liquid. We want to compare the buoyant force on each sphere and the magnitude of the tension in each rope. So we are given that these spheres would sink, so like the tension is supporting them. So we just got to do a force diagram. So we know that our forces, of course, we have a gravitational force on each sphere. And they are identical, so the mg is the same. And then upwards, we have a buoyant force, Fb, and we have a tension force, Ft. So we can see that sort of the buoyant force is going to tell us how much tension we need, because the buoyant force will help out the rope by some amount. So what is the buoyant force? Well, the buoyant force is equal to the displaced mass, which is rho v, displaced mass of the fluid, rho v, times g. Right? It's just the weight of the displaced fluid. So since rho 2 is larger than rho 1, F2 is larger than F1. Because I'm displacing the same amount of liquid in each case, except this is more dense liquid, so I have a higher buoyant force. So I must need less tension to compensate on y. So the buoyant force is greater on sphere y, so the tension is greater on x. So essentially what we have is we have like a large buoyant force here, so we need a small tension, but we have a small buoyant force here, so we have a large tension. This is a pretty classic problem, but it still is level 2 because there's some reasoning involved. All right, block of mass m is placed on top of a block of mass 2m. The coefficients of static and kinetic friction are mu s and mu k. There's no friction between the blocks and the ground. What's the maximum force that we can apply to the bottom block such that the top block does not slip? Well, this is a definitely like system of objects question. So whenever you have a system, the first thing you should do is just find acceleration. And I always call that the big box method, where you put your entire system into a box and figure out what forces are coming from outside the box. So here there's only one unbalanced force, it's F. So we can always just say that the acceleration of the system is the unbalanced external forces divided by the total mass of the system. So in this case, I'm applying a force F to a system of mass 3m. So this tells me that whatever the friction force is doing, it has to be able to apply this acceleration. So now we got to zoom into the box and we got to find the individual forces. So of course, this block can't just go to the right without a force accelerating it. So that actually tells us the frictional force acting on this block is going to point to the right. And it's static friction because it prevents sliding from happening in the first place, because these blocks are sticking together, so they're not moving relative to one another yet. So friction doesn't oppose motion, friction opposes sliding. And these two surfaces are stationary relative to each other. So this just says I can set the static friction force, its maximum value, equal to MA for that block. The maximum value of static friction is mu s times the normal force, which in this case is just going to be mg, is equal to ma, where a is F over 3m. So we end up getting the m's cancel, so we get mu g is equal to F over 3. So F is equal to 3 times mu static times g. I would rank that as hard. I'm going to maintain colors or people are going to get mad. Yeah, so this is a classic problem, this two-block system. All right, finally some break, so we get some graphs. These are generally less time-consuming. The angular velocity of an object as a function of time is plotted below. We're given the rotational inertia. Calculate the torque acting on the object at t equals 2. So we want torque. What are our expressions for torque? Well, we know one expression for torque is RF. Well, we know nothing about R or F, so it's not that. But we also know Newton's second law for rotation, which says torque is equal to I alpha. And we know we know I, which is 10. So we just need to get alpha. So anytime you have a graph, it's really important to kind of know like what the operations are. So if I read omega, I get angular velocity. If I slope, I get omega over t, which is acceleration, angular. And if I take the area, I get change in theta. So I want the slope. So alpha is the rate at which angular velocity changes. So at t equals 2, I'm just going to make myself this little slope triangle. So I gain 2 radians per second because I go up by 6 and over by 3. This is pretty standard. I forget what I called this. I forget if this was level 1 or level 2, but I'm guessing this was level 1. You just had to take the slope. Oh, more bar charts. All right. A planet is an elliptical orbit around a star. The kinetic energy K and gravitational potential U are shown at position X. We want the energy distribution of the system at point Y. So at point X, so this is X. At point X, we have some kinetic energy, and we have more gravitational potential energy. But remember, UG is negative. So if we actually look at what's going on here, our E total would be 1, 2, positive 2 units, and then 1, 2, 3, negative 3 units, so negative 1. So we have negative 1 units of energy total for this system. So now we got to figure out what graph could represent this system at point Y. So what we know is that U is equal to negative GMM over R. So if I'm actually going towards Y, my planet is getting closer to the star. So what's happening is my R is going down because I'm getting closer. So that means I'm getting a bigger negative number. So my U should also be decreasing. So I should look for a U that decreases and then an energy conservation. So I'm really looking for negative 4 bars of UG. And now I have to just figure out which one conserves energy, and that's going to be D, because the energy of this system is negative 1. The energy of this system is not negative 1. This is like negative 3. So some of these don't even conserve energy. Also, a way you can reason through that one without math is just think about it like dropping an object. If I get closer to the planet, my gravitational potential energy decreases, so my speed or kinetic energy should go up. So we know we should speed up. And Kepler's second law also tells you speed up passing point y. So you know it had to be one of the kinetics going up. I guess there's 3 of those, but yeah. All right, consider the following scenarios in which a block of mass m is pulled at constant speed along a rough horizontal surface, a distance d. We have these 3 different orientations of forces, and we want to compare the work done by friction in each scenario. So this is just a straight up work question. So work is equal to frictional force times distance for the 3rd time today. Lots of work on here. So we just got to figure out what that is. So what is friction? Well, we're on a flat surface, so we can just write it as mu k times normal force times distance. Friction coefficient is the same. Distance is the same by the setup, so we see that work is going to be proportional to the normal force. So we just got to rank the normal force acting on the block in each of these cases. So notice in this case, this is our base case where the normal force is equal to the weight of the block, because there's no vertical forces helping or fighting the weight. Scenario 2, part of my force is helping the ground push back up on my block. So in this case, the normal force is less than mg. And in this case, the rope is actually fighting the normal force. So the normal force is actually greater than mg in this case. So scenario 2, the frictional force is going to be lowest because the normal force is lowest. Scenario 3, the frictional force is highest, and 1 is in the middle. Even though there wasn't a whole lot of math with this comparison, I thought this was hard. Anytime you have to talk about normal force and comparing them, that's tricky for students. All right, a motion map for a pullback car accelerating from rest is shown below. Dots are spaced by 0.5 seconds. Find the magnitude of the average velocity and average acceleration of the pullback car over this interval. Okay, well, let's get the easy one out of the way. We know that the average velocity is just delta x over delta t. So this dot is at 2.0 seconds because 0, 0.5, 1, 1.5, 2. So we can just d over t this to get the average velocity magnitude. So I'm 1 past 15, so that's 16. So that's 16 centimeters in 2 seconds. So my average speed is 8 centimeters per second. Then we are given we started from rest. So we can just use kinematics actually to get the acceleration. Now, since we're starting from rest, the easiest equation to probably use is d equals 1/2 at squared. So I went 16 centimeters in 2 seconds. So I am solving 16 equals 2 times a. So a is actually also a number with 8 in it. So 8, 8, that is answer choice D. It's probably level 2 because you gotta do kinematics with this. If you try to do some like dot interval stuff, I'm not sure it quite works out. But I think you can eliminate this. I think you can eliminate that it's going to be 4 if you try other techniques. All right, 19. This is a classic. Solid disk has mass m and radius r. We are going to put these sort of clay balls at different spots around the disk. Scenario 1, they're halfway out. Scenario 2, they're all the way out. We want to compare the rotational inertia of each system about the center of mass. So it's either larger in scenario 2 or they're equal. So this is really hoop versus disk, right? Whenever you're asked to compare things with rotation, go back to the base case of hoop versus disk, because that's about how our mass is distributed. So a moment of inertia is not about mass. It's about how that mass is distributed. So our formula is that I for a system of objects is the sum of all the MR squareds. And notice in both of these cases, the m's are the same because I have a disk and 3 spheres. So I'm just really looking at r. So we see that the average r is greater in scenario 2. So that's just going to be A. So again, it's about how the mass is distributed. Like the masses are equal. So like the weight of this system is the same for each, but it's the rotational inertia. It's harder to get it rotating or to stop it from rotating. This is just what moment of inertia is, so that's 1 star. All right. I got 2 blocks moving together with a coupled spring, and then the spring is released, and we have some sort of collision. So this is definitely momentum. We want the magnitude of the impulse delivered to the block of mass m. So, given that we need the momentum change, we know that impulse is delta p, which is m delta v. Now, there's a really easy solution to this if you see it. Like our solution is probably going to take the full 2 minutes, but there's a really cool solution that if you know some things, you could get it pretty easily. So this is momentum. So we're going to say that the momentum before the collision equals the total momentum after the collision. Before the collision, I have a block m moving v to the right. Then I have a block of mass 3m also moving at a speed v to the right. Then after the collision, I have a block of mass m moving at some speed vf, I don't know. And then I have a block of mass 3m moving at a speed 2 to the right, so plus 2v. Then we can do our subtracting and combining, so we get 4mv is equal to mvf plus 6mv. So we get negative 2mv is equal to mvf. So vf is equal to negative 2v. So this means our original 1m block is going to move backwards at speed 2v. So that means this speed is 2v. And then we can just compute this. So the block's mass is m. My ending speed was negative 2v. My starting speed was v. So the delta, because I went from positive 1 to negative 2, so that's going to be negative 3 mv. And I said there's a quick solution to this. I'm still calling this 3 star because if you went through all this, it's very tricky. This is Newton's third law. The impulses are equal and opposite. So you could have just computed the delta p of this block and known that they're equal and opposite. So this delta p was 3m times 2v to the right minus 1v to the right, which is, as expected, plus 3mv. Right? Impulses are equal and opposite by Newton 3. A block is attached vertically to a spring. The block is given a small displacement and released from rest. Which of the following will increase the frequency of oscillations? We can do it on a horizontal surface. We can do it with a larger displacement. We can repeat with greater mass or greater force constant. So these two are out because it's only physical properties of the mass spring system that affect period. And it's more easy to see this because this is what we get from the formula sheet. T is 2 pi square root m over k. Nowhere in here does it say displacements. So the period is only affected by m and k. So I know it's going to be one of those two. So what does each of these do? Well, if we have a greater force constant, that increases the denominator for t. So this has a lower t. And if we have a block of greater mass, that increases the numerator in the period. So this is a greater t. And then the only other thing we have to do is we have to relate this to frequency, where frequency is just 1 over the period. So if you have a lower period, you have a greater frequency. You had to link 2 equations there, so I called it level 2. The block shown below is suspended by 2 cables. we want to calculate the tension in each of these cables. So this is just force balancing. So I got 60 kilograms here. So the mg weight force is 60 newtons. And there's only one force helping me get pulled up. It's the vertical component of the tension, T2. So the vertical component of T2 is 60 newtons. And now we have enough info to actually solve everything else. So we're going to be interested in this horizontal component because that's going to be the same as this horizontal component. And then we can use Pythagorean theorem to get this object. So to start, I would probably just set up the fact that, I don't know, let's use tangent maybe, that tan of 53 degrees is equal to opposite, which is 60 newtons, divided by adjacent, which is the horizontal tension component. So this means Tx times tan 53 is 60. So what is tan 53? I'm trying to think in my head what it's going to be. This is a 3, 4, 5 triangle, of course. So it's 4/3. So Tx times 4/3 is equal to 60. So 4Tx is equal to 180. So that means Tx is going to be whatever 180 divided by 4 is. 45. All right, and then by elimination, we actually know what the answer is going to be, because if T1 is 45 newtons and a component of T2 is 60, well, we know T2 can't be 60 because that's just one of the legs of the triangle. So you could Pythagorean theorem this and you'd see it's 75. Lots of steps involved, even though it's just Newton's first law. 3-star. The position x of an object is plotted below, which could be acceleration. So what could be the acceleration graph? So you have constant positive, constant negative, linear increase, linear decrease. Well, we're just looking at slope relationships, and you can't really jump, most people at least, probably can't jump 2 graphs in a row. So we got to generate V first. So we know that V is the slope of x. So we can create a VT graph here. So notice that we have a positive slope. Then we have 0 slope. Then we have negative slope. So we have a curve that starts positive, passes through 0, and then becomes negative. And the easiest way to connect these would just be a straight line. So then we just do one more chain, right? Acceleration is just the slope of V. So I just figure out what that is. Well, what's the slope of a line right here? That's just a constant negative value. So it's the constant negative one. I said this with level 2. Also, like, the super easy solution to this is saying, oh, this looks like falling. This looks like throwing an object, as I just tossed my pen across the room. And we know that an object that's in free fall experiences a constant downward acceleration of g. So you could have just done this by knowing that fact, which was kind of a feature I intended for that problem. All right, at t equals 0, an object with an initial speed 6 meters per second encounters a rough horizontal surface. If the coefficient of kinetic friction is 0.2 between the object and the surface, determine the stopping time. So anytime you're asked about time, it has to be kinematics. So we just need to solve for acceleration, right? Because forces don't relate to kinematics. So we got to figure out the acceleration first. So if we're on a flat surface, we know that our net force is going to be the helping forces minus the hurting forces. And if I'm moving along a flat surface with nothing pushing me, I'm getting no help, but friction force is hurting my motion. So my net force is just going to be the negative of the frictional force, which is mu k times normal force. So I can say that that's just going to be negative mu times mg. And then we can find the acceleration. Acceleration is just F over m. So that's just going to be negative mu k times g, which is 2 meters per second squared. And that's going to be slowing me down. Now we just do kinematics. So our initial speed is 6 meters per second. We want the stopping time. So we don't want the kinematics with distance in it. So we just use Vf equals V0 minus AT. So 0 equals 6 minus negative 2, or sorry, plus negative 2 times t. So t equals 3 seconds. You did have to do forces and kinematics, so it's a two-step thing here. This is a pretty standard question, though. Ooh, this is one of my favorites. The wheel shown below rolls to the right at constant velocity without slipping. Points x and z are on the circumference, while y is at the center. Rank the magnitude v of the velocity of points x, y, and z at the moment shown. So what we have to know about slipping, or rolling without slipping, is that the net result is v from the translation plus v from the rotation. So if I were to draw this, all the points on the wheel are going to be translating to the right at the same speed, and then there's going to be their rotation as well. So translating to the right means that all 3 points are going to have the same translational speed to the right. This would be like pure sliding. Then, if we look at the rotation, doesn't matter which way it's going. It's going to the right, so it's going to be rotating. It's going to be rotating this way. So that means we're rotating clockwise. So that means the top of the wheel would be rotating to the right, because again, that rotation is always tangent. Then there's no rotation at the center. And then at the bottom, we'd be rotating to the left to make that clockwise happen. So we see the net result here is going to be sort of our wheel, where we're going to have the vectors are additive at the top, then it's just the translational center of mass speed at the center, and then it's actually 0 at the bottom. So that would be x is the fastest, z is the slowest. 3-star. Understanding rolling conceptually is very difficult. I think most of us might know this fact that the point in contact at the bottom is instantaneously at rest at all times, but thinking about how the other two relate might be non-trivial. All right, looks like back-to-back hard questions looking at the size of these numbers. Ballistic pendulum, a crate of mass 9m is at rest. We launch a bullet at it. The bullet gets stuck in the crate. We want to figure out how high the center of the system rises. So a mistake is setting 1/2 mv squared equal to mgh before the collision. Because remember, collisions do not conserve kinetic energy, especially if you're burrowing into the crate, right? There's totally energy lost there. So what you have to do is you got to find the system velocity using momentum first. Then you can use energy. So momentum is conserved during all collisions. So I have a bullet moving at velocity v and nothing else. And then at the end of the collision, the bullet is trapped inside the crate. So I essentially have a mass 10m moving at some post-collision velocity. So this tells me mv equals 10 mvf, or vf is 1/10 of the impact speed, which should make sense because I essentially just multiplied my system mass by 10. And then we just conserve energy now. So now we can conserve energy because the collision is over. So I can just say the kinetic right after the collision is equal to the gravitational potential energy once the system stops. So 1/2 mvf squared is equal to mgh, where m is the system mass. So we'd get h equals vf squared over 2g, with vf being 1/10 v. So we get 1 over 200 v squared over g. Interesting. This is a involved problem, but it's very typical. I do give this 3 stars as a multiple choice because you have to know quite a few things. But I made the numbers work out nice enough. Right. Beam attached to a horizontal wall, or a horizontal beam is suspended from a wall. What is true about the force component from the wall exerted on the beam, along with justification? So we either have the wall does not exert a force on the beam, or the force is to the right. So just kind of looking at force analysis here, we know that we have an mg at the center of the beam, and we have a tension force to the left. But this beam is at rest, so all the forces must balance. So notice the forces aren't balanced right now because there's an unbalanced leftward force from the tension and maybe an unbalanced up or down. So you can't totally determine whether the wall is going to push up or down. It depends on sort of this cable angle. But we do know for sure that there has to be a leftward or a rightward component to cancel the tension. So we actually have to think about this differently, though, with the justification. I'm making us think about torque. The wall must exert a clockwise torque on the beam about the beam's center, or it's a counterclockwise torque. Well, if this is my center of the beam, the wall tension is trying to make me rotate with the clock. So the wall force must therefore make me, against the tension force, this is counterclockwise. The wall force, this is going to be clockwise. So it's clockwise. That'd be C. Biggest challenge, figure out what clockwise is. A constant force F is applied tangent to a disk of radius r for time t, and the disk completes 2 revolutions in that time. What is the change in rotational kinetic energy? So anytime you're talking about energy and forces, it's work energy theorem, except this time it's the rotational form. So the work done for rotational kinetic energy, the work done by a torque is delta K for rotation. And just like work done is force times distance, for the angular case, it's torque times angle. Because torques act over angles, force acts over distances. So we're just finding that the torque times the angular displacement. So let's do that. The torque is going to be RF, because we are just applying a force tangent to a disk. So torque is just R times F, because our technical formula for torque is F perpendicular times R, and it's entirely perpendicular. And then what is our delta theta? Well, it is 2 full revolutions. So this isn't 2. Delta theta is 2 full revolutions, and a full revolution is 2 pi radians. So this was kind of misleading that I gave you a t. The t isn't actually useful here. So 4 pi RF. You had to know about revolutions as well as just work energy, so that's why I made this 2-star. A crate slides horizontally with speed v off the edge of a table. What is the speed of the crate upon hitting the ground? So this is projectile motion, except it is a horizontal projectile. So what we know about projectiles is that Vx is going to be constants. So our x velocity doesn't change. But then to figure out our y velocity at the bottom, we can see that Vy, well, we can get Vy just by doing kinematics because our acceleration is g. We could say that Vy squared equals Vy0 squared, which is 0, plus 2 times our acceleration, which is g, times our distance, which is h. So you get Vy is square root 2gh. So again, we use the kinematics that v squared equals v over squared, v0 squared plus 2 times a times displacement. There's an energy approach here as well, but that's not as easy to see why this works. So what this tells us is now we have our speed in the x and we have our speed in the y. So we can just combine them Pythagoreanly to get our final speed. So this was v. This was square root 2gh. So our final speed is just this hypotenuse, which we can see it's this one. My goal is actually that you could have selected the answer to this, maybe just by looking at them, if you knew it sped up and you knew it had to be a Pythagorean relationship. Yeah, that's something I forgot to say as we go through this. This is a multiple choice test. If you figure out what the answer is, just circle it. I'm going through like the long approach. I'm pretending we don't have these like crazy insights to some of these things that'll trivialize them. All right, the two systems of objects shown below are each arranged into triangles. The first potential energy is Ux. What's Uy? Well, U is the sum of the pairs of negative GMM over R. So, because again, these are an energy debt, that's why it's negative, because all of these masses are an energy debt with each other, and we'd have to pay them energy to get separated. So, this is worth -1, 1 and 2 is worth -2, 2 and 1 is worth -2, so this energy is -5. Then over here, we have 2 and 2, which is worth -4. We have 2 and 1, which is worth -2, and we have 2 and 2, which is worth -2. So that energy is worth essentially -8 when we sum up all the pairs. So we have -5 GM squared over S and -8 GM squared over S. So notice the sign is the same. The sign is the same, but system 2 is 8/5 of system 1. I forgot if this was 1 or 2. I'd probably guess this is 2. Water flows from a wide section of pipe with radius 0.2 meters into a narrow section with radius 0.1 meters. The speed of the water in the wide section is 4 meters per second. Calculate the speed in the narrow section and find the volume flow rate. So this is just continuity, kind of like that first problem we did, where we know that A1 V1 equals A2 V2. These are circular cross sections. So my first pipe has cross-sectional area pi times 0.02 squared, pi r squared, and that V was 4. And then my second pipe, because we know that A is pi r squared for a circle, then my second pipe is very similar. It just has half the radius. And there is like a quick way you could have seen this just by looking at it. Because if we half the radius, we have quartered the area, so we have to quadruple the speed to compensate for that. So we get that V2 is equal to 4 times 0.02 divided by 0.01, all squared. So we see that we are going to get 4 times 4, which is 16 meters per second. And then pick your favorite one of these to plug in to evaluate the volume flow rate. The volume flow rate is just is just AV. So let's just pick, if you just evaluate this, you'd get, it's the 0.005 answer. I believe the other distractor is like not not doing pi r squared or something. Two blocks are connected to a pulley along a ramp as shown. First scenario, we got the ramp is frictionless. Second scenario, there is kinetic friction between the block and the ramp. In each scenario, the system accelerates and the hanging block moves up. Which of the following is true about the block's motion? So we got to compare all these things. So once again, it's probably helpful to big box method this. So we see that the net sort of external forces on this is we're going to get an mg from the hanging block. We're going to get an mg sine theta from the sliding block. And then since there is friction, we're going to get a friction force from the plane in scenario 2 at least. So what we can see here is that there's an extra force fighting our motion in scenario 2. So we actually know that F net in scenario 2 is lower. So this means there's a lower acceleration in scenario 2, which makes sense, right? If you add friction, the system should be accelerating at a lower rate. Let's see what we can gain from this. The total mechanical energy of the two-block system remains constant in 1, but not 2. Total mechanical energy of the two-block system. It's AP1, you know I had to do it. I didn't say the Earth, so A is false. The Earth is not part of the system, right? The blocks are rising and falling, so gravitational is doing something, right? There's zero energy right now in the two-block system. So as the blocks start moving, that energy changes. Now, it would be correct if I said two-block Earth system. In both scenarios, the mass of the hanging block must be greater than the mass of the ramp block. Well, notice that the hanging block pulls down with its full mg, but the ramp block pulls with mg sine theta, so only part of its weight. So that's actually false. Because if we're getting pulled upwards, that must mean there's a ton of mass on the ramp, right? Because I'm not driving my system that way. The hanging block rises to a greater maximum height in scenario 2. Well, there's no way that happens. There's no way that happens because that's going to relate to energy. That's going to relate to energy, and there's no way that the total energy, there's no way that more energy gets conserved in scenario 2. So by elimination, that makes it D. Why is that true? Well, we can see that F net on, this is just F net equals MA on the hanging block. So we see that FT minus mg equals MA. So the acceleration is larger in scenario 1. So the tension force must be larger in scenario 1. Yeah, this is definitely just difficult. A lot of evaluating going on there. The angular acceleration of a platform as a function of time is shown below. Which of the following correctly ranks the magnitude of the linear acceleration of the points on a point on the platform at each of these times? Well, anytime you have a graph question, you got to figure out how it relates. Is it a reading question? Is it a slope question? Is it an area question? Well, in this case, we're relating angular acceleration to linear. So we have the relationship, linear acceleration is angular acceleration times the radius. So we are literally just reading the graph. Oh, that's an interesting looking thing. My proportional symbol looks like my alpha. So we're literally just ranking the height. Because if your angular acceleration is greater, your linear acceleration is greater. So BAC. 1 star for that because it's just reading a graph. All right, 3 identical beams of length L are joined into this U shape. The horizontal beam is at y equals 0. Where is the center of mass of the system? So these are all uniform beams. It has to be in P1. So we can do our famous trick with center of mass if we just shrink all of the objects into dots. So what we really have is not this picture, but what we really have is going to be this one where we have a dot at 0, and then we have 2 dots at y over 2. Or L over 2, rather. Because again, the center is just going to be exactly halfway between the two of these. So then we can just do our center of mass calculation, where YCM is just going to be 1 over M total times the sum of M sub I, Y sub I. So we get 3 M's total. Then there's 1 M at 0. There's another M at L over 2. And there's another M at L over 2. So we get 1 over 3M times 2ML, or just, sorry, ML. So we get 1/3 ML. Oh, no. 1/3 L. Lots of misspeaking on this one. Now, I actually made this that you could figure it out without working it out, because I thought that was valuable to give you an answer choice. So you could have noticed that if these two beams were by themselves, the center of mass would just be halfway up at L over 2. But they're not. This beam is going to drag them down slightly. So the horizontal beam is going to drag the center of mass down, and it should be closer to 1/2 than it is to 0. So the only answer that has it below the midpoint is that one, and it's clearly not 0. It's clearly not that. A spring of length 8 centimeters and spring constant 5 newtons per centimeter is unstretched. Then we attach a block and we suspend it vertically. What is the new length of the spring? So I specifically did this one without a picture to make us think about it. So without anything attached, we have a length of 8 centimeters. Then it says we attach a block of mass 2 kilograms. And we want to find the final length. So what happens due to springs is we get an extension. So we just have to set our forces equal, because we know that there's going to be a gravitational force mg pulling down on the block, and then the spring exerts a Hooke's law restoring force k delta x. So we just say k delta x equals mg. So delta x is mg over k, which is mg is 20, k is 5, so we get 4 centimeters. Now we have to be careful, that's not actually the answer. This is how far the spring extends. So the extension is actually 4 centimeters. So this means our final x is just going to be 8 centimeters plus the extension of 4 centimeters, which is 12 centimeters. So is it a bit mean? Is it a bit mean of me to do that? Potentially. 2 blocks are attached to a pulley by a string. One block is placed on a frictionless table. The other block hangs off the edge of the table. We release the system from rest, and we want the work done on the string, work done by the string on the block of mass 4m after the hanging mass has fallen a distance h. Well, anytime we see work, there's sort of 2 ways of doing this. There's 2 ways, equally valid. You could say work is equal to the tension force times the distance traveled. I think we'll probably do this approach. And then you could also do this by saying work is delta KE as long as you do it for the 4M block. Both of these should work. And we have time, let's do both. So first of all, system of objects. So of course we know big box is coming. So the only unbalanced force on this system is the weight of the hanging block. So the acceleration of my system is just the net force on the system divided by the total mass. So I have mg driving, and then the total mass is 4m and 1m, which makes 5m. So I just get g over 5 is the acceleration. So if I do that, that allows me to easily find what this tension force is, because I can just set F equals ma. So Ft is just equal to ma for the 4m block. So that's just going to be 4/5 mg. And then we can find the work done just by multiplying that by the distance traveled, which is just going to be h. Because since the objects are connected, if the string falls a distance h that way, that must mean the string also went a distance h that way. So that's how you get 4/5 mgh. Now, if you wanted to do energy, that might actually be more efficient. You could just do mgh equals 1/2 times 5m times v squared. And you'd get v equals square root of 2/5 gh. And then you could just plug into the kinetic energy formula where you'd get k is 1/2 times 4m times v squared is 2/5 gh. And does that work? Yeah, it does. Cool. So I thought it was worth going over both solutions there just to show that it works out. All right. Oh, this one's a tricky one. Suppose a car is turning at constant speed in a circle of radius r. Consider the following 3 scenarios. The road is flat. There's static friction coefficient mu between the car and the road. Then in the other scenario, there's no friction, but we bank the curve. And then in scenario 3, we bank the curve and add friction. So here we're just using the fact that centripetal force is equal to mv squared over r. And we're trying to find which one has the greatest speed possible. So we see that this v squared is going to be proportional to the net centripetal force. So we just got to find what forces are contributing to the motion here. So in scenario 1, what's helping us go in a circle? It's a flat road, so it's just static friction. What about scenario 2? Well, in scenario 2, the whole reason we go on a banked curve or a ramp is part of the ramp pushes you towards the center of the circle. So in scenario 2, we get a component of the normal force. And then in scenario 3, if we have a banked curve with friction, it's both, right? We have friction helping us turn, and we have a component of the normal force. So think about turning as like traction, where these forces are helping give you traction. So if 3 is 1 and 2 combined, it has to be scenario 3. I thought that was difficult. Anything with banked curves is difficult. All right, now to conclude with some non-bad ones. A sphere is initially at rest when a torque tau is applied for a time delta t. The angular momentum is L1. Then we do the same torque for another delta t. Then we get L2. We want to find L2 over L1. So when we're talking about torque and angular momentum, we use the fact that torque, this is really impulse momentum theorem, but for angular. So we get delta L is tau times delta t. So we're just going to do this with multipliers. And we're starting from rest, so delta L is just L final. So in scenario 2, we apply the same torque for twice the time. So our angular momentum is just doubled. Now this one can be tricky because people automatically think about things like work and energy and think there's squares here where there's not. So this is actually quite simple. And if you do it by hand, like if you do this by hand and actually just do the ratio, you'd get tau times 2 delta t divided by tau times 1 delta t. And we see that that's definitely just 2. And last, we try to end with an easy one too. A ball is launched into the air at an angle theta above the horizontal, which is true about the velocity at the top of the trajectory and why. So is the velocity 0 at the top, or is the velocity non-zero at the top? So this is just our standard projectile motion, right? We know that horizontally, we do not change our motion because gravity is always directed down. We're always accelerating down at approximately 10 meters per second. But vertically, our speed is changing due to gravity, right? Because we have g. So this is literally just a standard projectile question. Horizontal speed of the ball remains constant. So I thought that was easy. We should definitely know that the speed does not stop, right? Your vertical velocity component is 0, but your speed is not 0, nor is your acceleration. So acceleration is g down at all times. Horizontal velocity is a non-zero constant at all times. And then it's only Vy that does the changing and turning around thing. All right, we did it. So we'll see. Obviously, I made some mistakes, as you'll see by the cuts. So I had to like refilm some parts. So I don't know if I came in under time or not. I feel pretty good about this. So I'd say this is on the medium. This is on the medium hard side for the time point of view. Concepts, I thought this was pretty fair, and it really did cover a good breadth of things. And the stuff that I was light on, I'm going to try to put in the free response to get us our good coverage. But hopefully that was a good review for you.